Chapter 13, Section 3, Multilayer Perceptron. Perceptron can express logic gates that we have seen in this lecture, AND gate, OR gate, and NAND gate. We can change the types of these logic gates by just changing the parameters, weight and threshold. We do not need to change the structure of a perceptron. In other words, a perceptron can be AND gate, OR gate, and NAND gate, depending on its weight and threshold. But how can we find the parameter values that enable a perceptron to be an AND gate, OR gate, or NAND gate? We can leave this work to a machine. In machine learning, we can have the machine find the parameter values automatically. We can do it by passing a training dataset to a machine and defining the learning model as a perceptron. Let me introduce another type of logic gate, XOR gate. XOR gate represents exclusive OR gate. It outputs 1 only when either 1 of x1 or x2 is 1. When both inputs are 0 or both inputs are 1, XOR gate outputs 0. As we saw, by setting appropriate parameters, we can create AND, OR, and NAND gate by a perceptron. However, we cannot express XOR gate by a perceptron. Why? Let's go back to how to find the output in a perceptron. We can find it by these expressions. Here, bias B and threshold theta are constants. So, we have only two variables, W1 and W2. Some of you may feel it as a complex operation, but let's transform the equation step by step. By transforming the formula, we can see a perceptron represents an equation of a straight line. It is the same form of y equals ax plus b. That is, a perceptron expresses a linear function. Let's consider a case of AND gate. The figure represents AND gate. There are 4 dots that represent the 4 points shown in the AND gate's truth table. The orange dot outputs 1, and the other green dots outputs 0. In this case, we can find a straight line that classifies the orange dot and green dots. Since it is a straight line, it can be created by a perceptron, suggesting that a perceptron can create AND gate. Next, let's consider a case of OR gate. The figure depicts OR gate, summarized by the truth table. 3 of the 4 dots output 1, and only 1 dot outputs 0. In this case, we can find a straight line that classifies the orange dot and green dots. So, we can say that a perceptron can create OR gate. Similarly, we can say that a perceptron can create NAND gate. It is obvious because the outputs of NAND gate is the exact opposites of those of AND gate. So, how about a case of XOR gate? For XOR gate, we cannot classify the data points by a straight line. Any single straight line fails to classify the orange dots and the green dots. But a curve can classify orange and green successfully. However, a perceptron is a linear function, so it can express a linear boundary, but it cannot express a non-linear boundary like this. If we can use two straight lines, we can classify the orange and green. It means that A combination of two straight lines can approximate a non-linear boundary. Each line is a linear function that can be expressed by a perceptron. So, we can create an XOR gate by combining multiple perceptrons. The upper one is an AND gate, and the lower one is an OR gate. We can use a various combination of perceptron to create an XOR gate. But here, as an example, let's apply a NAND gate first. The upper right dot outputs 0, and other 3 dots output 1. Let's apply OR gate for these 3 points. Only the 2 dots in the middle output 1. You can see that the result is equivalent to that of an XOR gate. Here, the orange dots meet the conditions of both the NAND gate and the OR gate. That is, these 2 dots are the products of the combination of a NAND gate, OR gate, and AND gate. It means that we can create an XOR gate by combining multiple perceptrons. Let's see the combination we saw in the previous slide by using truth tables. As we saw, we create an XOR gate by combining multiple perceptrons. Here, we reproduce the process in the previous slide by truth tables. So, first, let's input x1 and x2 to NAND gate and get the outputs. Here, let's call the outputs as S1, not Y, because they are not the final outputs. Next, input x1 and x2 to OR gate and get the outputs named S2. Then, input S1 and S2 to AND gate. We can get the final outputs Y. We can see that the relationship between the initial outputs x1 and x2 and the final output y can be summarized by this truth table that represents an XOR gate. The same process can be depicted by this figure. We can see that we can create an XOR gate by combining multiple perceptrons as a multi-layer structure. The set of these multi-layered perceptron is called a multilayer perceptron. Here, we use a NAND, an OR, and an AND gates, but we can use various patterns of combinations. Using a multilayer perceptron, we can define an XOR gate. Moreover, we can define more complicated non-linear boundaries using a multilayer perceptron. Thank you for watching. Please thumbs up and subscribe to my channel.